Okay, so in the last video, we started talking about continuity and the definition of continuity at a point for a function, and we looked at several different examples. We're going to kind of expand on that a little bit more. But in order to do what we want to do, we have to use something called the squeeze theorem. And I will actually throw out there, the squeeze theorem is a common type of theorem in math. It pops up a lot in a lot of the things we do. Those of you who are going to go on to Calc 2 and upper level calc like that, this will pop up repeatedly. It's an idea that works in a lot of different types of math. So this is probably, if you've only done pre-calc and trig, probably the first time you've really seen it. The problem is it's a theorem, but the proof of this theorem is beyond the realm of this class. It takes higher level math stuff. But we can at least state the theorem and then see how it works. And what it says is, let x sub 0 be an element of I. And we said before, I is just an interval, so it's just some interval I. Okay? Let f, g, and h be functions such that f of x, I don't know why I put the x sub 0 there, f of x is, your book uses less than or equal to, good. Less than or equal to g of x is less than or equal to h of x for all x in I except possibly at x sub 0. If the limit as x approaches x sub 0 of f of x equals L, which is equal to the limit as x approaches x sub 0 of h of x, then the limit as x approaches x sub 0 of g of x is equal to L. Okay. So let x sub 0 be, or x naught be an element of I, some interval. Let f, g, and h be functions such that f of x is less than or equal to g of x is less than or equal to h of x for all x in the interval, except possibly at the x sub 0 I care about. If the limit as x approaches x sub 0 of f of x equals L, which is also the limit as x approaches x sub 0 of h of x, then clearly the limit as x approaches x sub 0 of g of x, the one in the middle, has to be the same. And again, I'll point out, like I said, the squeeze theorem is pretty common, and it's pretty simple to think about. If you have a bigger thing and a smaller thing, and there's something in between them, if the bigger thing and the smaller thing squeeze down to something in the middle, it has to equal the thing in the middle. I mean, it's pretty straightforward, but actually proving it mathematically takes a little bit of work, and it's beyond what we know now. And I would point out, all things being equal, how we will use this in this class is more as something to just look at to solve a few problems, because most of the things we look at, the elementary functions we mentioned in the last lecture, we won't really need the squeeze theorem beyond maybe once or twice. So it is important, and it will recur over and over in math, which is why I mention it now. But it's more of an idea now, which makes sense, and then we'll flesh it out as we go. But again, just thinking about it graphically, the idea is, if I have some function, say, I don't know, we'll go with sine x. I want to know if f of x is continuous at x equals 0. Now again, I'll point out, if we know what the graph of the wave looks like, the continuity clearly works, so we're pretty much done. But for the sake of argument, suppose all I actually had was the unit circle. And all I knew about the definition of my trig functions was, well, I draw the unit circle. That's terrible, but I only care about the first quadrant, so don't worry about that. So I pick some arbitrary angle theta, and then you all know the trick. I draw this vertical right here. That's y. This is x. That's 1. And then sine of theta equals y over 1, which is y. Cosine of theta will be x over 1, which is x, but right now we'll just focus on sine because that's what I care about. And the question becomes, clearly at different points here, I don't want to make this picture too messy, but as I kind of go around the circle, it is obvious that my sine values will get bigger and smaller and will be continuous. But there might be an issue here at 0. I mean, if this is 0, what is over here? These negative angles, and what do those mean, and how does that work? And the proof of this is not all that challenging. I want you to look in your book to at least grasp the concept. But if you think about it, if this is theta right here, the angle, theta is this arc right here. So we'll just say theta is that arc right there. And the sine value is right here, this straight line. But clearly, the arc is bigger than that vertical line. And that would be true anywhere I drew it. The arc around the circle will be bigger than the vertical line straight down to the horizontal axis. Which means I can say theta is greater than or equal to sine theta. But then clearly, if I did the same thing, and now I have to go down to this quadrant, so maybe I'll expand on my circle a little bit. If I did the same trick down here and called this theta, or I guess negative theta, well then these values down here would hold the exact same. Sine of negative theta is less than or equal to negative theta. But now, if I take the limit as theta approaches 0 on this side, oh, here, I'm actually going to have to flip this, clearly these arcs right here will be less than 0 because they're negative. They're down here. So these arc lengths will be negative, which means I can say negative theta is less than or equal to sine of theta is less than or equal to theta. But now clearly, as these thetas get smaller and smaller and smaller, as I take the limit as x approaches 0, that one will approach 0. The arc lengths get smaller. This one, as the arc lengths get smaller, that'll also approach 0. Which means this approaches 0, that approaches 0, this is in between them. By the squeeze theorem, this thing has to be 0, which then will tell me that sine of x is continuous at 0, because the limit will exist and it will equal 0, and the function is defined at 0, and sine of 0 is 0. It is now continuous at the point. And again, I will point out that, yes, I'm aware that seems like a little bit cumbersome to prove something that you already knew was true, but I just wanted to do it for this one. I'm not going to do it for any other functions. To give you an idea of how we actually do things in math, we have to use these definitions. We can't just say, oh, that's like a wave, so we're good. We have to actually use definitions and theorems and prove things out algebraically. We will be doing more like this later in the semester, not necessarily with the squeeze theorem, so I just wanted to give you an idea of how these things work. But what that means is we can now say that, let's see, the limit as x approaches x sub 0, the limit as x approaches 0, I keep writing x sub 0. The limit as x approaches 0 of sine x equals 0. By the same token, using the same type of principle, you could show that the limit as x approaches 0 of cosine x is equal to 1. And I'm not going to do that one. And then from there, we'll shortcut some of the proofs that would probably be somewhat boring. We can then say that cosine and sine are continuous on the whole real line R, which, if we know what the graph of the waves looks like, was true. This is just the somewhat mathematical way of showing that it's true. Okay, then let's see. Okay, I'm going to end this video here. It's only 10 minutes long, but there's 2 more things we want to go over. And I'll just save those for one more video to kind of break this up for you and not try to cram everything in.